Hello, we are Team 1, and this is our final presentation for the course Intelligent Robotics. Our project was based on the paper Constrained Covariance Steering-Based Tube MPPI presented at the American Control Conference 2022. We'll discuss our detailed paper and code analysis and further replication and improvement process later in the presentation. But let's first discuss the background and motivation. Recently, there has been a rapid advancement in autonomous systems that demand efficient and reliable motion planning and trajectory optimization methods. For example, in applications like urban mobility, highway driving, or dynamic navigation, they all require efficient, safe, and real-time trajectory optimization methods. There are various computational approaches for this. Major methods are sampling-based methods, nonlinear programming, sequential convex programming, differential dynamic programming, and other hybrid methods. Among these, path integral method has emerged as powerful tools for sampling-based real-time trajectory optimization. This is a timely research field as evidenced by various case studies published such as autonomous vehicles, space robotics, and robotic manipulation planning. The most widely used method in the robotics and control applications is the Model Predictive Path Integral (MPPI) control method. Our chosen paper is one of its variations, Tube MPPI, which combines constrained covariance steering theory for discrete time stochastic linear systems with MPPI. It aims to enhance robustness against uncertainties and variations in system parameters while demonstrating improved performance and scalability in diverse control scenarios. This is a hierarchical classification of PI methods. Other central methods are cross-entropy method and PI to CMA method. CEM is a probabilistic technique used for refining control policies in an iterative manner. Its goal is to minimize the cost functions by leveraging a process called importance sampling, where it focuses on the most promising regions of the solution space. Over time, CEM has evolved into a family of algorithms, each with unique variations and characteristics. This approach combines PI control with covariance matrix adaptation. It is highly effective in dealing with non-convex or unknown cost landscapes where traditional optimization methods often struggle. This makes it well-suited for tackling complex optimization problems, especially in high-dimensional or uncertain environments. However, our main focus is on MPPI, and we'll discuss the details by the following speaker.
So now let's talk about existing methods in the paper. So first, let's introduce MPPI. So MPPI is an algorithm designed for optimizing control inputs in dynamic systems, particularly those facing uncertainties and disturbances. Through the core principles of simulation-based optimization, weighted trajectory evaluation, and an intuitive update law, MPPI adapts control inputs iteratively, leading to enhanced system performance. So now let's move on to the tube MPPI. In tube-based MPPI, there are two optimization layers, and the architecture is inspired by the standard tube-based model predictive and receding horizon control architectures. The first optimization layer corresponds to a vanilla MPPI algorithm, which uses a nominal plant or a nominal representation of the dynamics. The second layer comprises a different dynamic programming controller, which tracks the trajectory generated by the higher level optimization. So now let's move on to constrained covariance steering. It refers to a control strategy in stochastic systems where the goal is to guide the state distribution, represented by its mean and covariance, towards the desired target distribution, while simultaneously adhering to specific constraints on the state probability distribution, often expressed as chance constraints, which limit the likelihood of violating certain state boundaries. Essentially, it's about controlling the uncertainty of a system while ensuring the system stays within defined probabilistic limits. So there are two properties of CCS. First is controlling uncertainty. Unlike standard control methods that focus on the mean state, covariance steering actively manages the spread of the state distribution, which is crucial when dealing with systems subject to significant noise or uncertainty. Second is about chance constraints. These constraints specify a maximum allowable probability of violating certain state boundaries, adding a layer of robustness to the control design by considering the stochastic nature of the system. So here is the original implementation of the CCS algorithm. So CCS input requirements are the length of input sequence trajectory, then the first number of states in input sequence for Hall space generation are included. We'll also include problem horizon parameter. We also need to take into account set of observed obstacles or obstacle constraints in the environment. We also have matrix coefficients of a discrete time stochastic linear system, as you can see in line 11. We also have noise or disturbance covariance metrics associated with the system dynamics. And finally, we include predetermined threshold for covariance. So here is the step-by-step algorithm of CCS and PPI. First, the algorithm initializes nominal state and nominal covariance. Then, for iteratively over number of horizons, we compute MPPI and CCS. So first, MPPI generates a pair of reference state and input sequences. Then the state sequence is used to generate a safe convex region over which the constraints are satisfied with HS-gen algorithm or Hall space generation algorithm. So mean and covariance for CCS is initialized after that. After initializing those variables, CCS is run to compute the control trajectory, control covariance, and feedback gain. After that, control action for the current time step is initialized from the computed nominal sequence and feedback gain matrix. Is initialized with computed feedback gain value by CCS from the previous line. Then we update the control input. We updated control input are sent to the vehicle actuators. Then we do nominal state on covariance matrix updates. And finally, if the largest eigenvalue of the computed covariance exceeds a predetermined threshold, then the nominal state is set equal to the real state and covariance is set to 0. So now let's talk about some contribution and improvements. So first of all, we should talk about the track generation, which is important to have a list of waypoints following center line of track and generate obstacles as track limits on both sides. So red and blue circles are then applied as input to Hall space generation function, as you can see on the figure on the right. So the following steps are computed during the track generation process. We will first provide waypoints outlining the track flow. Then we create and smooth the track's convex hull. We then generate left and right boundaries by offsetting along the normal of the racing line based on track width, and we place obstacles at intervals along each boundary. So the paper's experiment uses a double integrator, which simplifies the system dynamics. On the other hand, we're focusing on a vehicle dynamics called bicycle model, as you can see in the figure below. So to be more detailed, bicycle model approximates the car as having just two wheels, front wheel for steering and rear wheel for propulsion. Wheelbase L is the distance between the car's front and rear axles, and we set it to 0.1 meters in our implementation for simplicity. So for simulating the system, we need to predict the future state of a car given its current state and control inputs. As current state, we give position of x and y, heading angle theta, and velocity. And the control inputs are acceleration and steering angle delta. Then we output the state derivatives using these inputs. And one of the challenges that we faced during the contribution of our model is we implemented CCS on nonlinear dynamics by testing linearization with MPC controller. The errors were compared with rollout to see how feasible the linearization approach and how much it deviates from the nonlinear path. So as you can see on the graph in the right, the graph shows that linearizing with MPC works reasonably well.
Now let's talk about replication and implementation. We have started the replication and implementation process with the original repository, which was attached to the paper we have chosen. To start with, the original repository has limited computational power, and we struggle testing and producing new changes to the dynamic system and cost functions. For instance, in the original implementation, running a simple MPPI algorithm for 256 samples and a horizon of 30 takes 3 seconds per iteration. Our implementation was rewritten using JAX and utilizing GPU, performs 30 iterations per second, which is almost 100 times speed improvement. Moreover, the original implementation to Rust-constrained covariance steering creates a separate optimization problem from scratch on each iteration, which also reduces the performance of the system. We have rewritten it from scratch, taking into account modularity and preserving the idea. After we have prepared our simulation setup, we have dived deeper into how each cost was implemented in the original repository, and have found that it was hard-coded for simple systems and environments only. So in order to test our application for car on racing track, we had to come up with baseline and almost start from scratch. The baseline we stick to is using car models in a racing track environment with or without obstacles. We use a set of waypoints to guide the car to progress further on the racing track. As soon as we get into the close proximity of the waypoint, we switch to the next one. Modification of the baseline will be introduced of angle regulation procedure using pure pursuit algorithm. One more problem we face is using CCS for nonlinear dynamics model. Although we tested linearization of dynamics on simple MPC problems, it didn't quite work for our scenario. We suspect there might be several reasons for that. Simple bug in our re-implementation, because there was almost no time to dive even deeper, and CCS becomes huge QP optimization when we introduce too many obstacles. We have tried to select only a specific subset of obstacles to consider, but for some reason, the problem remained infeasible. Thus, we decided to test our methodology of applying heading angle regularization technique against the usual MPPI. For the evaluation purposes, we have chosen 2 different racing tracks where all combinations of algorithm will be tested, with and without obstacles, with or without pure pursuit regularization. During testing process, we have encountered difficulties tuning MPPI parameters. For example, the combination of horizon we chose and average distance between waypoints highly depend on each other. If the horizon is not enough to be in close proximity for the next waypoint, algorithm may easily hallucinate and produce unreliable results. But thanks to our new implementation, we were able to test multiple parameters. To benchmark our solution, we have chosen the following metrics: number of passed waypoints, it shows how far our algorithm progressed, average speed during the run, and average distance for the center line from the current position. It shows how far our algorithm deviates from it. The results can be summarized in the following chart. We see that both approaches perform equally in terms of average distance to the center line, but proposed approach, pure pursuit for angle regularization, highly damages average speed and thus the number of passed waypoints. We suspect that it is due conservatism in heading angle regularization as it influences sampling process and worsens the performance. We didn't provide the showcase, but expect that under disturbance it produces more stable solution as heading angle is more constrained. However, we have to point out again that the tuning of hyperparameters of MPPI is a highly complicated process, and some choices may diminish the contribution of pure pursuit regularization and even contradict with which resulted in poor performance. To summarize, in our term project, we have tried to apply a paper on CCS MPPI to the nonlinear dynamics of bicycle model and enhance it with analytical methods. However, at the end of the project, we didn't yet were able to apply CCS as expected, but we can propose a methodology that possibly can tackle this problem, and this can be future research. First, our team believes that CCS can be reformulated for nonlinear dynamics, precisely similar to MPC and nonlinear MPC formulations. Second, there might be a bug or a problem with our implementation using linear approximation, but it is subject for more investigations. We believe trying to merge conventional approaches with modern control paradigms is important in order to constantly seek for new solutions to existing control problems. Thank you.